Hey, what's up you lot? Parth here, back at you with another video. This time my hair and my beard are even longer than my previous video because somebody said that my hair and beard were getting too long. No such thing. In today's video, I want to talk to you about something known as the wave equation. It looks something like this, but don't worry, you don't need to have a mathematical background to understand what I'm going to be talking about. As long as you've studied physics to high school level or even maths to high school level, then you should follow exactly what I'm saying, and by the end of this video, hopefully you will have some understanding of what this equation is trying to tell us, and why it's called the wave equation. Before we go any further though, I'd quickly like to say if you enjoyed this video, please do leave a thumbs up and subscribe to my channel if you haven't already. Leave me a comment down below telling me which equation you'd like me to explain next because I really like making these equation explainer kinds of videos. Anywho, all that aside, let's get into it. Let's start by labeling a few variables that we see in the wave equation here. Specifically the variables x and t. Let's get the easy ones out of the way first. X refers to a spatial direction. Let's say for our purposes that the x direction is toward the right. What this means is that along this line we have different values of x. X is equal to 0, x is equal to 1, x is equal to 2, and so on and so forth. The units don't really matter, we just need to know that this is a spatial direction. And t, as we'd expect, stands for time. This is because we'll be studying the behavior of waves as time progresses. So we can choose a particular instance when we're studying a wave. We can choose t is equal to 0 to be now, for example, and then we can work out what happens to a wave that we're studying, maybe, I don't know, 5 units of time later, maybe 5 seconds later. And so basically just labeling these two quantities, we'll be able to understand one simple thing about the wave equation. It might seem like a relatively obvious point, but the wave equation studies the behavior of waves in space and in time. In this case, we've got what's known as the one-dimensional wave equation because we've only got x, which is the x direction, one dimension. Now, other letters that we can see in this equation are u, d, and c. Out of these three letters, c is the simplest one to explain here. C is simply the speed of the wave that we happen to be studying. So if we're studying an electromagnetic wave, maybe a light wave, then c is simply the speed of light. Moving on to u. U is known as the displacement of the wave, or specifically the displacement of different parts of the oscillating wave. Because for example, if we think of a wave that moves like this, and if we just focus on one particular point of that wave, one particular point in space of that wave, we see that even though the wave is moving from left to right, the point is moving up and down. And so when this point is, let's say, at this position, we say that u is equal to 0. As it moves upward, we say that u increases, and as it moves downward, we say that u decreases. In other words, u is the displacement of this point in, let's say, the up and down direction. The only letter that we haven't yet discussed in this equation is d. D is not actually a variable. D is not something that takes a value in this equation. The d's are simply there to tell us that there is something known as differentiation going on in this equation. So what's differentiation? Well, one way to think about differentiation is that it's a really useful tool in helping us understand the rate at which objects do things. For example, we could plot a graph showing us how a car moves from one point to another over some time. So what we've got here is the position of the car on one axis and the time on the other axis. What we're seeing here is that at t is equal to 0, at the beginning of the car's journey, the car is at a position x is equal to 0. And as we progress through time, as we move from left to right on this graph, its position changes. In other words, like we said already, at t is equal to 0, the position is x is equal to 0, and then later on its position changes, and what we've got here is a curved graph. But instead of just being able to tell what the car is doing in terms of how its position changes over time, we can use differentiation to tell us something about how fast the car is moving. Because specifically on this graph, the gradient or the slope of the graph at any point tells us the speed at which the car is moving at that point in time. In other words, if we were to find the gradient or slope of this graph at this point here, corresponding to t is equal to 5 seconds, then what we would find is the speed at which the car is moving at t is equal to 5 seconds. And what we see is that this car is constantly speeding up. It initially starts out very, very slow because the gradient is flat, and then as we go further along to the right, the gradient increases. So the speed of the car is increasing over time. It's speeding up. So to help us understand this better, what we can do is to actually plot the gradients of all of these slopes as time progresses, rather than the position of the car as time progresses. At the beginning, like we said, the gradient was 0, so at t is equal to 0, we get gradient is equal to 0, and then as time progresses, the gradient increases. In other words, as time progresses, the gradient is getting larger and larger and larger. So this is the graph that we end up plotting. What we've actually plotted is time on the horizontal axis, and like I said earlier, it's the speed of the car that we've plotted on the vertical axis. But technically, this speed is actually dx divided by dt, or as it's pronounced normally, dx by dt. What we've done is we've differentiated the car's position with respect to time. And specifically, if we differentiate an object's position with respect to time, then we find its speed. And actually, interestingly, in this case, if we differentiate the differentiated quantity, if we differentiate speed now with respect to time, then we find the car's acceleration. In other words, if we were to find the gradient of this graph at every point in time and produce a new graph where we plotted all those gradients as time changes, then we would see that in this particular case, the gradient of this graph stays constant for all times. It doesn't change, which means that when we differentiated the speed, we find a flat line because the gradient is constant at all times. And here what we've actually found is the acceleration of the car. Many of you might be familiar with this idea where we take the distance traveled by an object and then we produce a graph that shows the speed of the object and we produce another graph that shows the acceleration of this object. However, you may have only done it in terms of an object that is, say, moving at a constant speed, so you don't have to worry about changing gradients. Well, this is where calculus and specifically differentiation comes into play. Differentiation can deal with the fact that the gradients of our initial function are changing. But the important thing to take away here is how we took gradients at different points along the graph and plotted the values of those gradients to give us the differentiated quantity. And this has been a very, very brief overview on differentiation. I'm not going to go into too much detail here. If it is confusing, by the way, let me know in the comments down below, because understanding the rest of what I'm about to say kind of hinges on the fact that you've sort of understood what I've just said so far. So I really want to make sure that what I've said so far is clear and understandable, and for that reason I'll leave some useful resources in the description box down below so that you can understand differentiation a bit better. But please do feel free to ask me in the comments below if I haven't explained anything clearly. So with all of that in mind, let's consider a wave now. Let's say it's a really simple wave, like we said earlier, a transverse wave, where it's moving like this from left to right, and a particular point along that wave is actually oscillating up and down. We can even think of this as a wave on a rope, for example. Let's say one person is holding on to an end of a rope and they just wibble it up and down, then what we'd see is this kind of transverse wave. Anyway, that's enough world building. Let's just imagine that we've got this mathematical function that looks like a sine curve, if you're familiar with sine curves, rather than thinking about waves on a string or anything physical like that. This is a wave that's moving from left to right over time. Well, let's assume that we can take a snapshot. Maybe we take a camera and we take a snapshot of this wave at a particular time. That snapshot of that wave looks like this. Now what we can do is to be really nerdy, be physicists basically, and assign coordinate axes to this wave. In other words, the x direction is toward the right, and we'll say its displacement, its vertical displacement, is up and down. Because we're going to assign x and u values to every point along that wave, and we're going to use these values to mathematically calculate something about the wave's behavior. Now notice what we've done. We've plotted u on the vertical axis and x on the horizontal axis. Let's differentiate u with respect to x. Remember what that means? Essentially finding the gradient of our wave at every single point and then plotting that gradient. So let's start with x is equal to 0. That's this particular position in space. So we see that at this particular point, the gradient is quite steep. Therefore, it has quite a large numerical value. And then let's say at x is equal to, 1 meter, we see that the gradient is 0 because what we've got here is a flat line. So we plot that onto our new graph where we've got the differentiated quantity on the vertical axis and x on the horizontal axis. And then we repeat this process for multiple different points along our wave, but realistically we do this for every single point along our wave. What we get is something that looks like another sine wave, but slightly shifted. This is technically a cosine wave. But now, this is not a wave in real space anymore. This is not something that's actually oscillating. This second graph that we've created is just a mathematical function, whereas the original wave is actually a wave moving through space. We had just assigned it an x-coordinate and a vertical displacement u-coordinate. But then at this point, what we can do is we can take our graph of du by dx and x, and then differentiate it again with respect to x. This gives us what's known as d2u by dx squared. It's basically just doing the differentiation process again. Or some people like to say d squared u by dx squared, which I'm not used to, so I'm not going to say that anymore. And so what we've done is we've taken our original wave and we've generated a mathematical function from this wave that's equal to d2u by dx squared on the vertical axis and x on the horizontal axis. This seems to be getting quite abstract and mathematical, but bear with me, things will hopefully start to make sense soon. What we've done so far is we've taken a snapshot of the wave. Remember we did that earlier? We took a photo of it as it was moving through space so we could see how it was behaving at one particular point in time. That's the time at which we took the snapshot. Instead, let's now do the opposite thing. Let's now consider the behavior of one particular spatial point as time progresses. If we take one particular point in space, let's say, I don't know, x is equal to 8, then let's see how this particular point behaves as the wave moves from left to right. We see that initially it starts out at u is equal to 0, but then as the wave moves from left to right, we see that point moving up and down. Now what we're going to do is to plot another graph. This time we've got time on the horizontal axis and the vertical displacement u on the vertical axis. And we need to be careful here because this graph we're plotting is not an actual physical picture of the wave. This is just a plot of what this particular point, this red point along a wave, is doing as time progresses. And we see that at t is equal to 0, it starts out at u is equal to 0. And then as time progresses, let's say at t is equal to 1 second, for example, we see that the u value has decreased to the lowest possible value, and then as the wave continues to move, we see that we've produced another sinusoidal pattern. Now remember, like I said, this graph that we've produced of u and t is not actually a physical picture of the wave, it's just a description of what our red point along our wave is doing over time. And it might be confusing to see so many different kinds of sine curve, or at least sinusoidal curves, but remember, the only one that is actual physical picture of what was going on is the original wave here. Anyway, so we've got this picture of what this particular red point is doing as time progresses and the wave moves from left to right. Let's differentiate this graph with respect to time, not just once, but twice. What we're finding is d2u by dt squared. Now, you might be seeing where we're going with this here. We found d2u by dx squared earlier, and we've just found d2u by dt squared right now. As it turns out, both of these mathematical functions, remember, both of these mathematical functions are sinusoids, they look like sine curves, and so we could, in principle, by some basic mathematical processes, equate d2u by dx squared and d2u by dt squared. Because these two functions are sinusoids, because they essentially have the same shape, you should be able to see that we could, in theory, equate these mathematical functions, either by stretching or shrinking one of them or doing something to both of them. And specifically what the wave equation is telling us is that when we take d2u by dx squared and multiply it by the square of the speed of the wave, then we get d2u by dt squared. In other words, what we're finding here is that a sinusoidal wave is a possible solution to our wave equation. Another way to think about this is a sinusoidal wave moving at a very specific speed through space, the speed being c, is a solution to the wave equation. It obeys the wave equation. And there are some very important constraints to be made here about exactly what we put as an argument of our sinusoidal wave function. Basically, it's not as simple as having just a sine x or a sine of t function. Remember that the oscillation, uppy-downiness of the wave depends on not only position, but time as well. Because earlier what we did is we took a snapshot at a particular time, and we also looked at the movement of one particular point in space at all times. But if we want to describe this whole wave for all particular points along the entire x-axis and for all different times, then we need to worry about the wave being a particular function of both x and t. And exactly what function of x and t we have is going to be related to the speed of the wave. For example, here is a possible solution of the wave equation. I'm not going to talk through it because it's quite advanced, but if you understand differentiation, pause the video and check it out. When you do, you'll see that we've got these quantities omega and k in our argument of the sine function, which specifically are known as the angular frequency and the wave number of the wave. These are very important quantities for a wave, and in this particular case we can see that they also relate to the speed of the wave. But like I said, that's way too advanced, I'm not going to go into huge detail here. Now here's the thing. This wave equation that we've been talking about so far is quintessentially known as the wave equation, but there are lots of different wave equations. Specifically, this is a classical wave equation in one spatial dimension. Classical because it's not accounting for any effects of relativity or quantum mechanics. This describes all sorts of things such as mechanical waves, light waves, sound waves, and so on. You just switch out the value of c for the particular speed of the wave that we're thinking about. But like I said, this only describes classical waves, waves that have been known about for years and years. An example of a different wave equation is actually the Schrodinger equation. The Schrodinger equation describes how the wave function of a quantum system behaves over time and space, and like I said, that's a wave equation with very, very different qualities. So this is my brief description of what the classical wave equation is about. Certain things that I haven't gone into are the fact that it's known as a second-order linear partial differential equation. Second order simply because we're differentiating our quantity twice, both with respect to x and with t. Linear because our equation only deals with u, it does not deal with any powers of u, such as u squared or u cubed or anything like that. Remember, the d2u by dx squared only tells us that we're differentiating u twice. We're not having to deal with differentiating like u squared twice or anything like that. And it's a partial differential equation because technically these d's are partial derivatives. Remember what I said earlier about the vertical wibbliness of our wave being dependent on both what position of the wave we're considering and at what time along the wave's journey we're considering. But partial differential equations kind of split this dependence up into separate chunks. We see on one side we're only dealing with the dependence on time, and on the other side we're only dealing with the dependence on position. And these curly d's tell us that we're dealing with just differentiating with respect to x and ignoring completely anything to do with t, and then vice versa. So, this is a second-order linear partial differential equation describing classical waves. As if I haven't thrown enough words at you yet. Listen, like I said earlier, if something doesn't make sense to you, if I'm just throwing words at you that don't make any sense whatsoever, then let me know in the comments down below and I'll try and clarify. And of course, if I've got something wrong, then please do let me know down below as well. I'd like to correct this by leaving a comment down below and pinning it so that you guys can read it and not go away with incorrect information. For the time being though, that's all I have for you on the wave equation. It's a very basic, very hand-wavy overview of the wave equation, or rather the classical wave equation. But I'm hoping that for those of you who aren't undergraduate physics students, you'll get a bit of a sense of what the wave equation is trying to do. And remember that although sinusoidal waves, the ones that we've talked about in this video, are a very valid solution of the wave equation, they're not the only solution to the wave equation. So with all of that being said, let me know in the comments what equation you'd like me to try and explain next. But for now, I'm going to end this video here. Thank you so much for watching, and thank you so much for all your support. I really appreciate it. I'll see you really soon. Bye.